Hello, I am Luca Nessi and I am a PhD student of Politecnico di Milano. I'm presenting my work on the growth of ultra-thin magnetic films on graphene with the purpose of exploiting them for spin polarimeter experiments and in particular as an application for spin and angular resolve photoemission spectroscopy. Here there is the outline of my talk. I'm giving you some motivation for this work and explaining the physical principle underlying it. Then I will move through the presentation of the growth process on suspending thin films and the characterization of their structural reliability. Then I'm presenting a mechanical and a magnetic characterization of these devices. And finally, I will move to the conclusion. So the idea is to build a device which is able to do a selective transmission of the incoming electrons. So starting from an unpolarized electron beam, we have a selective transmission according to the fact that their spin is parallel or antiparallel to the magnetization vector of the active magnetic layer. So spin polarimetry exploits this filtering process of such a device in order to measure the spin polarization of an incoming electron beam, and in particular to quantify the number of electrons with a definite spin direction. Another application of these devices is in spin and angular resolve photoemission spectroscopy, as I said before. This is a very well-known technique to study novel classes of materials, and here you have electrons outcoming from a sample, which are dispersed in energy and in angle, in order to reconstruct the energy band structure of a crystal. So if we can reach the three-dimensional control of the magnetization vector in these devices, joined with the embedding into a two-dimensional matrix, like here, we could in principle avoid a point-wise measurement, which is which is the actual state-of-art technology we have in this kind of field, and have a one-shot two-dimensional image, a fixed energy of the whole bulky space with a spin resolution. This kind of project was conceived in collaboration with the APE beamline in electrosynchrotron of Trieste. So in order to grow these kind of freestanding membranes, this is the generator structure we used. So composed by a high robustness material, for the case is graphene, so the membrane must support the whole heterostructures, avoiding corrugation or cracks. Then the overall thickness must not exceed 10 nanometers. This is because the transmission of the electrons exponentially decrease with energy, but also with the thickness of this kind of multi-layer. And then the magnetic layer, which is the active part of this kind of device, must guarantee, of course, the magnetization direction tuning in order to reach the 3D control of this kind of structures, then an high coercive field in order to guarantee stability of this kind of device, and of course also a high magnetic resonance. So for the choice of materials, as I said before, for the first layer we choose graphene with different thicknesses from 2 to 8 monolayers. Then for the active magnetic material we choose cobalt for the in-plane configuration of the magnetization, and an heterostructure composed by tantalum, cobalt, iron boron, and MgO for the out-of-plane configuration. Then for the capping layer, in order to avoid oxidation of this active magnetic material, we choose gold or ruthenium. So we start with commercial graphene 10 grids with different number of monolayers, and since these devices are very fragile, we want to understand the role both of the deposition process and of the handling of such a device in the damages reported. So we had this workflow with two SEM analyses before and after the deposition process. And we also test two kinds of growth technique, which are molecular beam epitaxy and magnetospattering. Here are three different outputs of such a workflow, which are an intact membrane, a completely damaged membrane, and a 98% intact membrane. So even if this last device is broken, it could be still suitable for our purposes, since the 98% of the surface is intact. Here we have the same analysis on about 30 devices. So for the pre-deposition image, we have a clear contribution of handling in the percentage of broken membranes, which for the case of 2 monolayers is around 10%, and it is a little bit smaller for the case of the device with 6 to 8 monolayers. Then the post-deposition analysis amplifies this kind of observation. In particular, we have 1/2 membranes which are broken for the case of 2 monolayers, while we have around 20% of broken membranes for the case with the 6 to 8 monolayers. What actually increases, and it's very clear from this graph, is the variability of such an output, in particular for the thinner case. So since we are interested in disentangling the handling contribution from the deposition process contribution, we normalize the data obtaining this graph here. We also separated the data according to the deposition process between molecular beam epitaxy and magnetospattering, and we can notice that for the case of 6 to 8 monolayers with magnetospattering technique, we can reach a survival rate of about 95% with a sufficiently small variability, and this would be the case we would analyze this in the following. Here I present the atomic force microscope characterization of this kind of suspended membranes. Here we have the topographic analysis of these membranes, since we want to avoid any kind of corrugations and also cracks in these devices. We do a topographic image of this, the different technique we employ, so between molecular beam epitaxy and magnetospattering, and we see that there is kind of a large variability between the roughness of the two surfaces, but both of them are smaller than 1 nanometer. So even if molecular beam epitaxy seems to be the best one for the roughness of these devices, also magnetospattering is still good as roughness under 1 nanometer. We also do a kind of force spectroscopy of this kind of membranes in order to understand which is the fracture load of this kind of devices. So we place the tip of the AFM in the center of the membranes, and we apply force to this kind of membranes to see which is the response of such a device, and we see an elastic response. Here there is a graph which is force versus the indentation depth of the tip, and we saw that there is an elastic response and a fracture load which is at 7.2 micronewton for the 6 to 8 monolayers, which is a high fracture load. So even if we have a lot of small broken membranes, this device is kind of robust. Since we are dealing with the suspending structures, we do a magnetic characterization measuring the Faraday effect with this kind of setup. So we have laser polarized at 0 degree, then the sample is placed between 2 coils, then we have a photoelastic modulator, then another polarized at 45 degrees, and then the photodetector. We have 2 kinds of heterostructure, as I said before, for the in-plane and for the out-of-plane configuration, and we have these 2 configurations in order to detect the out-of-plane component for this case and the in-plane component for this other case. So these are the two results for the tantalum, cobalt, iron, boron, MgO heterostructures, which is the out-of-plane one, and for the gold, cobalt, gold, which is the in-plane heterostructure. And we see that we have an hysteresis loop with an easy axis for the out-of-plane component in this case, and hysteresis loop with an easy axis in the in-plane component for this other case. And we obtain a coercive field which is 30 Ørsted for the case of the out-of-plane, and up to 40 Ørsted for the case of the in-plane in plane configuration, and of course for both of them a non-zero remanence magnetization, which is what we want to obtain for this kind of device and which is suitable for our purpose. What comes next is the characterization of the spin filtering properties of such devices. For this aim, we will tap an electron gun with gallium arsenide photocathode with negative electron affinity in order to obtain a spin polarized electron beam with energy between 0 and 30 electron volt, which is the typical range for a photoemission spectroscopy experiment. And with the collector after the device, which is actually a Faraday cup, we will count the number of electrons transmitted, and in this way we could characterize the selected transmission of such devices. So coming to the conclusion, I have shown you a presentation about the optimization and the deposition process of thin magnetic heterostructure on suspending graphene in order to realize freestanding magnetic membranes employed for spin polarimetry. In particular, we have designed a process which guarantees two different heterostructure with out of plane direction of the magnetization and in plane direction of the magnetization, and we have done a sort of realization of a matrix of these freestanding magnetic membranes with a sufficiently high survival rate of about 95% embedded in a metric scheme for spin polarimeter experiments. What comes next in terms of perspective is, as I said before, the spin filtering characterization of these membranes, and of course the realization of a matrix of membranes in which there are different directions of the magnetization in order to test it in a real setup of spin and angular resolved photoemission spectroscopy experiments. So thank you for your attention.